subject. Okay. So in the last lecture, we have studied about the mass theory, right? We also studied about the mass structure. Then we studied about the threshold voltage. Mass structure and symbol, right? Then we also studied about the mass operation, modes of operation, you can say. Okay, so this is all about the we have studied in the last lecture. So what we are going to study today, we will discuss here. So in today's lecture, first of all, we will see the background of mass structure once again. That is the background. Background of mass structure. Then we will see the biasing of MOS transistor. Then we will see IV characteristics of MOS. After that, we will see, after IV characteristics, we will see the energy band diagram. Energy diagram of MOS structure. Then we will see, we will find the width of derivation exactly. Derivation, the first derivation will be the width of depletion region. And second derivation will be to derive the width of inversion layer. So what is inversion layer? Anyone remember? Then lastly, we will solve one numerical. Then lastly, we will see a brief introduction about the MOS capacitor. So anyone remember the width of inversion layer? Sorry, what is inversion layer? Yes?
Sir, that is due to the minority carriers that are attracted.
So what are the conditions for voltage?
The VG is greater than VT.
VG is greater than VT.
VT.
It means that gate voltage should be greater than threshold voltage, right? Very good. So now let us start with the structure. So see the MOS structure. Everything you can understand by drawing the MOS structure. This is very important. So let us draw the MOS structure. So what happens in case of MOS structure, just we have to see here. Right? So there is a metallization. This is metallization for this is known as metallization for contact. Contact, right? So here we are doing the metallization for surface contact, right? Because this is p-type substrate, right? If you remember. So now there will be a two region inside the bulk p-type semiconductor, that is this is n plus, and here it will be also n plus, right? Again, on the top of the surface, there will be a silicon dioxide. Okay, this will be like that. So this is metallization. And this layer is insulator, you can say, or oxide layer, you can say. So this is oxide. So let us talk about oxide is SiO2. And again here there will be a metallization through the etching so that you can get the contact to the N region. So this terminal is known as source, and here again there will be a metallization. So this layer is known as gate, right? So which is represented by G, and here this terminal is known as drain, which is represented by D. So let us talk about this this is a semiconductor. So let us say this is silicon. Why silicon I am talking about? Because in most of the industry we use silicon to fabricate the MOSFET, or you can say BJT. So the gate material, if I talk about the gate, so the gate may be metallic in nature, or as I said, it may be polysilicon, right? That is heavily doped. So heavily doped means it will act as a perfect conductor, or it may be polycrystalline. So any doubt here? Okay, so now we need to understand this structure. Here we are not providing any bias, right? Bias means here we are not providing any voltage between the terminals, right? So here no biasing, right? So no biasing, it means that this structure or the device is in under equilibrium. Under equilibrium, right? Okay, so this structure, this is a p-type material, and here we are having the n dop. So what does it mean, the n plus? Heavily doped, right? Okay, so what will happen? So there is a p-type semiconductor here, and here there is a n-type semiconductor. So in that case, what will happen? There will be a depletion region, right? So now I would like to ask you all, wait a moment. If you recall about the semiconductor, what happens in case of semiconductor when, let us say, you have P and N region. Let us say you have P and N region. Let us say this is P and this is N. So let us say this is N plus. Okay. So at the junction there will be a immobile ions, right? So where the depletion region will be higher, this is known as W, and W is the depletion width. So as you can see that in the P side, the width of the depletion region is larger as compared to N plus region. So why does it happen? Anyone can explain?
Sir, because of diffusion.
Because of
So the
diffusion.
number of charges should be equal.
So here, what happens, not because of number of the charges, here the concentration, that is the concentration of electrons, or you can say the charge carriers, is very, very higher as compared to the concentration of holes in the p region, right? So there will be a strong diffusion from n to the p side. So what will happen because of that? The diffusion region will be width will be higher, or you can say larger in p region as compared to the n region. So similarly, what will happen here? In this case, so depletion region will be higher, or you can say larger towards the p region, right? Because n plus region is heavily doped. So this is the depletion region. Depletion region. Okay. So now let us move towards now we will connect the biasing to the device. So what will happen in that case? We will look at it. So let us draw another diagram, mass with biasing, right? So what will happen? Just let us look at. So in this case, so let us draw once again the structure so that, okay, here it will be p type. There are two regions, that is n plus and n plus. So here let us say this is ground, or you can say at negative potential. So there will be a silicon dioxide layer here. Okay, so now there will be a etching. Through etching, we will get the contact to this n region. So let us say this is source, and here it will be this will be a gate. Okay, and again here there will be a etching, and through etching we will get the contact to the drain side. Okay, so now there will be a depletion width here. So we know from the last class we are not going to apply negative voltage to the gate. If you will apply negative voltage to the gate, then what will happen in that case? Anyone can recall?
Accumulation.
No, yeah, accumulation. So we don't want accumulation, right? We want inversion. So if there will be inversion, then what will happen in that case? In that case, there will be a formation of channel so that the current will flow from source to drain, right? So what is our conditions? The condition is, what is our desired condition? We want inversion, right? So inversion means, okay, so here we are connecting the positive. If you see here, this is known as VGS. So what do you mean by VGS? VGS is equal to VG minus VS. So it means that the gate terminal is connected to the positive terminal of the battery, and source side is connected to the negative terminal of the battery. Okay, now let us talk about the VDS. Another voltage is the VDS, that is this is plus minus, so this is VDS. So VDS will be equal to VD minus VS. So where VD is positive and VS is negative. Now overall we will connect to the substrate, or you can say body of the terminal. So here, okay. Now I would like to ask you here, what will happen? See here, what we have to observe. So in the last, okay, so since this is n plus region and this is p plus region, so there will be a junction, right? N plus p junction from the source side, and also on the drain side there will be n plus p junction. So what will happen because of that? There will be a diode, right? Yes or no? So here there will be a diode, right? Yes or no? In the last lecture I already taught you.
Yes, sir.
Okay. So now here what will happen? This is the biasing. This is the MOS transistor with biasing. So we have to remember how we can do the biasing. So for the N, basically this is all about the NMOS. So if for the NMOS, the gate voltage will be positive, right? So now let us talk about the case 1. So in the case 1, what will happen? Sorry, wait. Okay. So we are interested in case 1, that is for the case 1, what will happen if the VGS is less than VTH? So what is VTH here? Or VT, you can say threshold voltage. Threshold voltage. So now let us talk about this condition. What will happen to our device? So let us once again, we will draw the device, draw this device structure so that you can understand what will happen to the device. So here, once again, we will draw. So this is P type. N plus region, and again here will be a silicon dioxide, that is insulator. Okay, so there will be a metallization here, or through the etching we can make the contact. So this is drain, this is SiO2 layer, SiO2 silicon dioxide, and here it will be a gate, right? So here you can see the condition, that is drain. Oh, drain and source can be interchangeable, but here we will write the same fashion as we have done earlier. So just see here, this will be the source and this is drain. So the configuration of this, the biasing will be like that. This is VDS and this is VGS, okay, and here we will connect the overall negative. Now what will happen here? The VGS is less than VTH. So if you remember the second mode, what was the second mode of operation? Anyone remember? What will happen if the VGS will be less than VTH, but it is greater than 0?
Depletion.
Depletion, right? Very good. So what will happen in that case? So let us see the depletion region. Now the depletion region will be like that. Right? So here what will happen in this case? You have to remember, in this case, since VGS is less than VTS, so there will not be any significant flow of current from the source to drain, but still there will be some current. So in this case, the current I will be very small, right? So this region is known as, so why this is very small? Why the current is very small here? And VTH is the voltage, or you can say potential for inversion. So why the current is very small for VGS is less than VTH? Because here still we are not getting the channel between the source and drain. So here still the channel is absent. So because of that, there will not be any flow of electrons from source to drain. As a result, what will happen? The current flowing from source to drain will be very, very less. Right? Any difficulty? Here the current is very small. Okay, so just write it. Current is very small, is very small because the channel is not formed between source and drain. Okay, so if I ask you in the questions for the VGS greater than 0 and VTH, the current is very small, and what is the reason behind it? So your answer will be, this is because the channel is not found between source and drain. As a result, the electrons will not flow, electrons will not move from source to the drain. As a result, what will happen? The current will be very less. Any difficulty in understanding this concept? Yes?
No, sir.
Okay, so now move to the case 2. So case 2, in case 2, what will happen? The VGS will be less than VTH. Okay. So what will happen in that case? Let us draw the diagram so that you can understand. Why I ask you whether do you understand or not, yes or no, because so that I can understand whether you people are understanding or not. So based on that, I can repeat. Yes.
So for the case one, if the channel is not formed,
Mhm.
how could we observe this small current even?
Here, the case 1, right?
Yes, sir.
Okay. So the case how can we?
Like
Okay.
you said, the
Yes.
current will be very
Okay.
small.
Okay. What will happen? So because of the positive voltage at the gate, so there will be some negative charges here, right? So it will attract little bit magnetic carriers from the p side, because in the p-type semiconductor, what will be the magnetic carriers?
Electrons.
Electrons, right? So it will attract towards the surface of the junction, but still it will not penetrate this depletion layer because of the majority charge carriers p holes is still there, right? So there will be a very less current, negligible current, you can say, or you can say reverse saturation current. This small current is equivalent to reverse saturation current. So have you heard about the reverse saturation current? Yes?
Yes, sir. Yes, sir.
Yes. So this current will be equivalent to the reverse saturation current, right? So now you got my point?
Yes, sir.
Okay. So now move to the second case, that is when VGS is greater than VTS. So what will happen in that case? Okay. First make the, so under this case, what will happen? There will be a strong inversion, right? And where there will be inversion? Right? Do you remember? Yes, you can say where there will be inversion for this case. We have already studied about this in the last lecture. Yes, you can say. So what will happen in this case? In this case, okay, we can see for the VGS greater than VTH, then in this case, here there will be VG, and here there will be a drain. So the connections will be like that. So the positive terminal will be goes to the drain side, and here also VGS. So here you can observe very closely that from here there is a formation of, still there will be a depletion region, no doubt, but here when the VGS is greater than VTH, so what will happen? There will be a strong inversion. A strong inversion means there will be a flow of electrons from from source to the drain. So as a result, what will happen? And this region is known as N channel. N channel. Okay. So what will happen here? So whenever the VGS, that is gate to source voltage, is greater than the threshold voltage, then there will be inversion at the interface, so that there will be a formation of channel. So as a result, what will happen? The flow of electrons starts from source to drain. As a result, there will be a flow of current, right? So what is happening here? First point you can write, whenever the VGS is greater than VTS, there will be inversion, right? Inversion at the interface, or you can say surface, or you can say near the junction. Near the junction. So as a result, flow of electrons occurs from source to drain. So third point will be significant amount of current flows from source to drain. So why it is happening? Why the channel is forming between source and drain whenever the VGS is greater than VTS? What is the reason? Because what will happen here, there will be a strong negative carriers, right? Sorry, the strong positive carriers because of the positive applied voltage. So because of the positive applied voltage at the gate, there will be a strong attraction of magnetic carriers from the p type. Magnetic carriers will be electrons, right? So there will be a strong attraction of electrons from the p type semiconductor at the surface of the metal oxide semiconductor layer interface. Then as a result, what will happen? There will be a formation of channel. Thereby the current will start flowing from the source to the drain. Any doubt here? Yes? Yes, you can say if you have any doubt. No one can speak. Yes? Before?
So clear.
Okay. So now move. So what will happen here? there is one more concept here. Here, if you see case 1 and case 2, we are just varying VGS, right? But what about VDS? We have not yet varied the VDS, right? So let us talk about the case 3, that is case 3. Case 3, here what will happen? Here the condition is already the first condition, that is already this is VGS, get to source voltage is greater than VTH. Now here next we will vary here the VDA, that is drain to source voltage. So what will happen to the device? We will see here, drain to source voltage. So see here what will happen. If you see the diagram here, if drain is connected to the positive terminal of the battery, right, and p-type semiconductor is connected to the negative side of the battery, so what will happen? There will be a reverse bias here. Means the diode, that is N plus, here the N plus P, right, diode will be reverse biased, right? Reverse biased, correct? What will happen? So if you will vary the VDS, that is drain to source voltage at the drain side, so okay, so at the drain side, the N plus P diode will be reverse biased, right? So as a result, what will happen? As a result, there will be pinch of the channel at the drain side. So pinch off means shrinkage, or you can say reduction of the channel at the drain side. So pinch off, let us say pinch off means that reduction of channel at the drain side, right? So what will happen because of the pinch off? So because of the pinch off, what will happen because of the pinch off? The current, the drain current, you can say the current, that is ID, will start saturating. So what do you mean by saturation? The saturation means constant current, right? So let us draw the diagram so that you can understand what is pinch off. So the diagram of the MOSFET under the pinch off will be, so when the pinch off will occur? When the VDS is very larger, right? So let us draw so this is N plus, this is N plus. So here there is insulation layer, okay, so insulation layer, so this is SiO2, and here we will do some etching to form the contact, metal contact. So this is source, this is drain, this is gate, this is drain. So whenever you will make, okay, the connections will be like that. So here the VGS, so if you can observe here, so this is depletion region, and here this region is, okay, let me draw, change the color so that you can identify. So this, you can see shrinkage of channel towards, so this is known as pinch off, right? So pinch off means when the VDS is very high, then there will be pinch off of channel, right? Channel at the drain side, right? So as a result, what will happen? The current I becomes constant. So why the pinch off is occurring for the higher voltage? Can you explain? Just few minutes ago, I explained why it is happening. So just I am expecting the answer from your side now. So what will happen if you will increase the VDS for a particular value? Then what will happen? There will be a pinch off. But why pinch off is occurring? Yes? Anyone can answer. Don't feel shy. Yes, Aditya?
Sir, because the N plus P diode is reverse biased.
Yes, very good. So now, if you any doubt in understanding this concept?
No, sir.
Okay, so now let us move towards the IV characteristics of the MOSFET. This is very important to understand. So IV characteristics. Okay, let me change the color. Okay. Of MOS transistor. Okay. So let us talk. Okay. So here, so IV characteristics here, first of all, we will draw the IV characteristics for ID, that is drain current. Drain current versus drain to source voltage, that is VDS, for different gate to source voltage, right? So here we have to see and understand the characteristics, IV characteristics of. Okay, so let us talk. So on the x-axis there will be VDS in volt, and here there will be 0. And on the y-axis there will be a drain current which is in milliampere, let us say. So actually usually the range of the drain current is in milliampere. So let us mark that is 5, or you can say here 10. On the VDS, let us say that is 10, 20, 30 and 40 volt, let us say. So what will happen when the VGS is less than VTH? Anyone remember what will happen whenever the VGS is less than VTS? Then what will be the amount of current? Yes,
It's a very small current.
Very
small
less
current,
amount of
yet
current.
like reverse saturation current. Okay, so the flow. Okay, let me change the color. So for that, what will happen? The current it will be very small from source to drain. So it is nearly parallel to the x-axis. So this is when the VGS is very less than VTH, right? What will happen if we will increase the VGS greater than VTH? Then in that case, there will be a increase in the drain current, right? So let us draw the current for the VGS is less than VTH. So let us say this. Okay. So for this region, you can see what you can observe from 0 to 10, what you can observe, there is an increase in current, right? After that, what will happen? There will be a pinch off for the further increase in VDS and current becomes constant. So let us say this is VGS is equal to 5 volt, which is greater than VTS. What will happen if you will further increase the gate to source voltage? Then you can observe that there will be a further increase in current, right? So for this particular value of VDS, you can say that the drain current is increasing. But what will happen if you will further increase the VDS? There will be a pinch off and the current becomes the constant, right? So this is known as, let us say this is for VGS is equal to 8 volt. Similarly, we can draw the IV characteristics. Let us say this is for VGS is equal to 10 volt. So for this region, you can say that the current ID, the drain current is increasing with respect to drain to source voltage. However, for this region, what is happening? This is known as, okay, this is known as saturation region. So this is known as saturation region, right? And however, this is known as what? This is known as linear region. Right? Any doubt here? So the voltage at this particular point will be the pinch off voltage, right?
So,
Yes.
will the pinch off happen in case VGS is less than VTH?
No, because there will be very small current.
So that will keep on increasing after that, not completely constant, right?
Yes, yes. Keep on increasing. No, this will not increase. You can see very small current, very small. You like reverse saturation current in nanoampere, or you can say picoampere.
Okay, sir.
Right? So any difficulty in understanding the IV characteristics? There is one more characteristic which is known as transfer characteristics. Transfer characteristics and CV characteristics. CV characteristics means capacitance versus voltage. So we will talk about it in the next class. Now we will talk about the energy band diagram of MOS structure. So here, okay, see here, understand from the IV characteristics. So for this region, in the saturation region, we are getting the constant current with respect to voltage source, right? Voltage drain to source voltage, right? So for this region, for the saturation region, the MOS device maybe act as a constant current source, right? So you have heard about the term voltage source, current source, like that. So for this, in the saturation region, you can see that the MOS transistor may act as a constant current source. However, what is happening in the linear region? In the linear region, the resistance is varying, right? However, in the saturation region, the resistance is, yes, resistance is constant here. Okay, so if you do not recall, what is resistance? What is the formula to calculate the resistance? Yes, anyone can say it. What is the formula to calculate resistance? Yes, can you recall? Just you have to apply V by I, right? Voltage, ratio of voltage to current. So you can also write in such a way that I by V. Oh no. Yes, I by V. Oh no, no, no. Wait. So you can say that I by V, exactly, inverse. That is true? Yes or no?
Yes, sir.
Yes,
Okay.
sir.
So from the
Sir.
graph, let us talk about the IV characteristics here, right? Let us say this is V, let us say this is I. So if the current is varying in such a way that, right? So what will happen to this region? If you see this region here, the current is varying with respect to voltage. For what for region, what is happening? Here the current is I constant, right? I constant. And here I is varying. So what does it mean? It means that here if you take the ratio, okay, let us talk about this region. So if I talk about this region, so you can take any point, any 2 points in this region. So what will happen? Here let us say this is I1 and here let us say I2. Here let us say this is V1 and here let us say V2. So for this region, the dynamic resistance, that is R, is equal to change in current by change in voltage, and you can take the reverse, right? Inverse, sorry. So you can calculate in this way the resistance. Any doubt here? So what is delta? It will be I2 minus I1 divided by V2 minus V1, and you have to take inverse. Any doubt in understanding this concept here? Yes? So this ratio is known as the slope, right? If you remember, for the linear line also, if you want to find the slope of this line, and then what you do that? Just take 2 points, right? This is basic mathematics. So what will happen for this region? Let us say up to this region, what is happening from, let us say this point 1 to point 2. What is happening? Here the resistance is varying, right? Because current is varying. But for this region, what is happening? The slope is constant. Slope is almost constant. So the I will be constant here. So I will be constant. As a result, the slope will be constant here. Or you can, right? Any doubt? Okay. So it's already 11:55. So do you like to continue or I should stop here? Because topics are remaining to study. What do you think? Should I continue or should I stop here? It will depend on your wish. We can continue in the next lecture. Stop. You can speak. Don't write. Okay, so thank you so much. No problem. We will stop here, but still the topics are remaining to study.
Excuse me, sir.
Yes.
Sir, in case 2, the point number 3 which you wrote,
Mhm.
So you wrote that the electrons will also move from source to drain as well as the current shall also go from source to drain. So
The
isn't
flow of electrons, basically the flow of electrons, not for there will be a flow of electrons in the channel, not
so
from source to drain. This is just, yes, because of the inversion layer. So when there will be a flow of electrons occurs, so as a result, what will happen? There will be a flow of current from source to drain. Okay, so shall I stop the recording? Okay.